starting with our term. So period is going to be capital T. That is going to be the time for one wave, and that is going to be measured in seconds. Next is our frequency, which is lowercase f. That is the number of waves per second. So in 1 second, how many waves go past? That one is literally number of waves divided by the number of seconds. So dividing by seconds, that's called hertz. And wavelength is the length of one wave. So a couple different ways you can get the wavelength. That can be from equilibrium, like this. It can also be equilibrium down and then up. That's the same. It can be the crest up to the crest again. It can be the trough down to the trough again. Those would all be examples of full waves. Drawing a transverse wave. So transverse is going to go up and down. So this would be a transverse wave. The amplitude, so I'm going to dash line through the center. So amplitude would be this distance right here. That would be my amplitude. Or it can be the equilibrium down. That's the same distance right here. Crest is the top point, and trough is a minimum or bottom point, like that. Which of the following points have destructive interference? So if we look at A, that's both positive and positive, so that would be constructive, they would add. Negative and positive, that's destructive, so definitely point B, because they're in opposite, their displacement is in opposite directions, down versus up, so they would subtract. And then C is up and up, which is again constructive, so it's only B. Student is sitting on the edge of the swimming pool. They repeatedly dip their foot in and out, making waves that move across the water. They dip their foot slowly at first and then start doing it faster each time to the same depth. So depth that you're making your wave go to, that's going to be the amplitude, so that's the same amplitude. Faster isn't talking about the velocity that the wave is sending, like that the wave is moving through the water. They're saying they dip their foot faster, which means you're sending more waves each second, which means that my frequency would increase. My velocity, the wave velocity, is actually going to stay the exact same because that depends on the medium. And we're still in water, so it depends on medium, which would just be the water, so that's going to stay the same. Now, I know my frequency is increasing. Period is just 1 over the frequency. So if I'm increasing frequency, that's dividing by a bigger number, which means a smaller period, so this would decrease. Wavelength, so if we look at our equation, V equals F wavelength, well, we know that I have a higher frequency, and we know that this is staying the same, so that means this one has to decrease to compensate for that, so this would have to decrease. Alright, these are two sound waves. How would they sound different? Well, if you look, they have the same frequency, same wavelength, because they have the same length right here, but this one is a much taller wave, so this one would be a loud wave, and this one would be a quiet wave, but they have the same pitch. So A, or the first one, would be louder than this one. A wave, this is the speed, so V. The crests are 20 meters apart, so if I have a crest and another crest and the distance between them is 20 meters, then that is my wavelength. So V equals 5, wavelength equals 20. I want to find frequency and period. Well, I can just plug in V equals F wavelength. Velocity is 5. Frequency is what I'm looking for. Wavelength is 20, so I'm going to divide that over, and I should be getting 0.25. So my frequency is 0.25 hertz. And then if I want to find my period, well, period is just 1 over frequency, so 1 over 0.25, that should be getting me 4 seconds. Right, you stand by the railroad tracks as a train passes by. You hear 1,000 frequency while the train approaches, and 800 when the train is at rest. So while it's at rest, that's the true frequency or the source frequency. This right here is the observed frequency, what I hear. My source is the train, and you are the observer. We want to know how fast the train is moving, so I'm looking velocity of the source. And we can assume, oh no, I don't need to assume. It says you stand, so the observer velocity is 0. So I'm going to plug into my F equals V plus or minus V over V plus or minus Vs, times V source frequency. So we're going to plug in FO on the outside, 1,000, equals, this is going to be 343 on top and bottom. We're looking for VS. VS goes on the bottom. VO is just 0, so we can ignore it. And then 800 is on the outside. And this one, it says as it approaches, I'm hearing this as it approaches, that's going to be a minus sign on the bottom. Right, and this is like my X right here. So the first thing I'm going to do is I'm going to divide that 800 over. So divide 800 over. And that gives me 1.25 equals 343 over 343 minus VS. Now I have an unknown on the bottom, so I want to multiply it up, but I can't multiply just the VS, so I'm going to multiply this entire thing. So 1.25 times 343 minus VS equals 343. And then now I want to get rid of the 1.25, divide it over. That leaves me a 343 minus VS, divided. That gives me 274.4. Subtract the 343 over. That gives me negative VS equals negative 68.6. And then we're going to divide the negative out, so then that's our answer. 68.6 meters per second. This rope right here, it's going up and down, so that's going to be a transverse wave because I'm getting crests and troughs. If I get compressions and rarefactions, that would be longitudinal. This one, again, a transverse wave is moving to the right. And I want to know what is the motion of point P as the pulse passes. Well, the definition of a transverse wave is that it moves, like the points move perpendicular to the wave direction. And I know that my wave is going to the right, so if my wave is going to the right, what's perpendicular to the right? Well, up and down. So B. Now, a lot of people want to do D because they're like, yeah, it's going up and down, but it's also going to the side. But that's actually not true. When the rope comes right here, the rope is going to go up and down. It's not moving to the side. The same way in a stadium wave, like, I'll make my fingers standing. No, this is not going to work. Okay, if people are standing in the stadium, right, they like will go up and down, it goes across. This is terrible, that's everything. Anyway, imagine you have a stadium wave. The people don't move across the stadium to the side, right? They just stand up in their seat, and that creates a wave that goes across the stadium. The individual people actually stand up and down. All right, we're watching an ocean wave at the dock. They noticed 10 waves in 30 seconds. So sometimes seconds is your period, but that's not the period. Period's the time for one wave. That's the time for 10 waves. So those aren't any specific values, just the number of waves in a certain amount of time. They noticed that the distance between successive peaks is about 4 meters. So from one peak to the next peak is 4 meters. So then that's my wavelength. So I have a wavelength of 4 meters. That actually kind of gave me the wavelength. I want to calculate frequency and period. Well, frequency is the number of waves per second. So 10 waves in 30 seconds. That's going to give me a frequency of 0.33 hertz. Once I have frequency, period is just 1 over the frequency, so that would give me a period of 3 seconds. And those are reasonable, right? 10 waves in 30 seconds, that's 3 seconds for each wave. Okay. And then lastly, to find your speed, well, speed equals frequency times wavelength, so frequency is 0.33 times wavelength of 4. So that's going to give me a frequency of 1.33, or sorry, velocity of 1.33. That's your answer. How would these waves sound differently? So if you look, they're the same amplitude. So because they're the same amplitude, that means that they're going to be the same volume. So one is not volume, not volume. So one is not louder than the other. They're the same volume, same loudness. Now this one is much more squished together. This one has a higher frequency than this one. So this one will be higher pitched. And that one would be lower pitched. But again, same volume. How many wavelengths? So I'm going to start here, up, down, back at the equilibrium. That's 1, 2, and just a half. So 2.5 waves. Periodic waves struck by a tuning fork. The amplitude would be greater if the tuning fork. So we're talking about a sound wave. A tuning fork is going to send out a sound wave. So an amplitude is going to sound louder because amplitude has to do with volume. Higher frequency would just sound like a higher pitch. This would sound lower pitch. I want it to be louder, so I'm going to strike it harder. Have more displacement from equilibrium. Diagram below shows two pulses. What is the superposition when they meet? So these are both positive displacements. That's going to be constructive interference when they meet. So it will be like this, but it will be a height of 15 centimeters because when they meet, they're going to add up amplitudes. Period, if you have 4 waves in 10 seconds. So 10 seconds is not my period because that's the time for 4 waves, not 1 wave. So I'm going to do frequency is the waves per second. So 4 waves in 10 seconds. That gives me a frequency of 0.4. Then once I have that, period is 1 over frequency. So 1 over 0.4, and that is going to give me a period of 2.5. The only way to change wave speed is to change the medium. Changing the frequency doesn't do anything. Change the wavelength doesn't do anything. Only the medium tells me the wave speed. So that could be going from one string to a rope, or going from air into water, or anything where the wave is literally traveling through a different substance or object. All right, wavelength is equal to the distance. Okay, so let's look, A to G. I am back at the same point, but I have up, down, and up in there. That's actually 1.5 waves, so not that one. C to E, that's only half of a wave. B to F, that looks, yep, I'm ending the same point. I've got up and down in there, so that's correct. And then D to F is, again, only half of a wave. So which of the following are separated by half of a wavelength? A to B, nope, that's 1/4 of a wave. C to E, yes, that is half a wave. B to F, that's a full wave, and D to G would be like 3/4 of a wave, so no. A longitudinal wave moves to the medium, blah, blah, blah. The motion of the particle at point C, so the definition of a longitudinal wave is that the points move parallel, or oscillate parallel to the wave. So here, I know my wave is going to the right, because it tells me, so then parallel to that would just be right and left. That's awesome. One wavelength would be, so the same way for a transverse wave we do from crest to crest, or we do from like equilibrium to equilibrium, or even like if this were to continue from trough to trough. So for our longitudinal, we don't have crests and troughs, we've got compressions and rarefaction, so I can go from compression to compression, or rarefaction to rarefaction. So let's look, A to B. That would be going from like one side of the compression to middle of the rarefaction, so that doesn't make sense. A to C, that does make sense because I'm going from the right side of compression to the right side of compression on the next wave. So that is correct. B to C, that's going from a rarefaction to the other side of a compression, that doesn't make sense. And B to E, that's going from the middle of a rarefaction to like not the next compression but the one after that, so that doesn't make sense either. Right, you're standing on a dock and observe a piece of wood floating. As a water wave passes, the wood moves up and down, rising to the top of a crest every 5 seconds. So 5 seconds is my period here because I'm getting a crest, one crest to one wave each 5 seconds. That's my period. To calculate the frequency, I would just do frequencies 1 over a period, 1 over 5, so that gives me a frequency of 0.2 hertz. And then to find the wavelength, or sorry, speed, I just do frequency times wavelength. Well, frequency is 0.2, we just said. So now I need to know the wavelength, and if you look from crest to crest, oh look, that has a distance of 2. So that has a velocity of 0.4 meters per second. All done. That's your velocity. Should label it. The musician plays a note with a period of 0.005 seconds. If this is the sound speed traveling through air, what is the resulting wavelength? So I want to use V equals F wavelength. I know my velocity is 343. I'm looking for wavelength, but I need to know what my frequency is. But if I have period, well, frequency is 1 over period, so frequency is 1 over 0.005, so that gives me a frequency of 200. And now we just say 343 divide over the 200, and that's going to give me 1.75 when I divide over. 22, based on this diagram, we're going to determine the wavelength of each wave. So this right here is half of a wavelength, so if I want the wavelength, the full wavelength, that would have to be more than that. It would be a wavelength for A of 24 meters. B is super easy because this is one wave right here, so then it's one wave is 12 meters. C, this is one wave right here, so only part of the 12 meters is a wave, so I need less than 12 for sure. My answer is going to be less than 12. And then I'm going to say, okay, well, wavelength, I can just do the number of meters, the meters divided by the number of waves. I've got one wave right here and a half, so I'm going to do 12 meters divided by 1.5 waves, and that's going to give me 8 meters. And then the last one is pretty easy because I want this wavelength right here. And then I have 12 meters for 2 waves. So if 2 waves and 12 meters, one wave would just be 6 meters. So D would be 6 meters. If these were strings playing a note, which one would have the highest pitch? Well, highest pitch is just the highest frequency. So a high frequency is squished together. It has a short wavelength. So the one that's most squished together, the shortest wavelength would be D. If the speed of wave D is 48, what would the frequency of the wave be? Well, V equals F wavelength. I know my velocity is 48. I'm looking for frequency, and I already know my wavelength, right? We calculated up here. Wavelength of D is 6 meters, so that gives me a frequency of 8 hertz. What would the fundamental frequency be? So fundamental frequency means the frequency of the first harmonic. I know the frequency of the fourth harmonic, and if you look, if we think about what we learned, well, we know that this is F1, F2 is just twice that, F3 is just 3 times that, F4 is just 4 times that. So if this one has a frequency of 8 hertz, the fourth harmonic, the first one just has 2 hertz. This one would be 4, this one would be 6, because they're each just a multiple of 2. First one is 2, second one is 2 times 2, this is 3 times 2, 4 times 2, etc. So the first frequency is 2 hertz, this one would be 4 hertz, and this one would be 6 hertz. A wave takes 3 seconds to complete one cycle, so that's the period, the time for one wave. What's the frequency? So the number of waves per second. So 1 over 3 seconds, that gives me a frequency of 0.33 hertz. I get a third of a wave each second. This is a transverse wave because it goes up and down. Getting crests and troughs, not compressions or refractions. The frequency of this wave is 5 hertz. What's the speed? So speed equals F wavelength, so 5 times I need my wavelength. Now, wavelength is the length of one wave, so if I look, I've been given 15 meters, and that is for, this is one wave and a half. So if I have 1.5 waves in 15 meters, to find the wavelength, I'm just going to divide the meters by how many waves I have. And then that's going to give me 10 meters, which is totally reasonable. If this is 15, then this could definitely be 10, right? Makes sense. So then I just plug in wavelength of 10, so then V is 50 meters per second. Highest frequency to lowest frequency. So highest frequency would be the most squished together. This one, lowest frequency, would be the most spread out. And it's possible some of them are equal. So definitely B is the most squished together. Now these ones kind of hard to tell just by looking, so I counted up waves. This has 1, 2, 3, 4 waves. 1, 2, 3, 4. So these two are equal. This one has 1, 2, 3 waves in the same amount of time. So this one's slightly more spread out. These are slightly more squished together. So B, A, and C are equal, and then D is the last one. Largest wavelength to largest to smallest wavelength. So the largest wavelength would be with the most spread out wave, which is D. Then A and B would be the next one. And then, A and C. And then B would for sure be the smallest wavelength because look how long one wave is here. And now if you're wondering, wait, how did you know this earlier? So for D, from here to here is one wave, whereas from here to here, which is slightly smaller for A and C. So longest, these two are equal, and this one's the shortest. Largest period to smallest period. So remember, period is just 1 over frequency. So the largest period is the one that has the smallest frequency, and the smallest period is the one that has the largest frequency. So I already did highest to lowest frequency, so if I want biggest period to smallest period, I just flip this, it's opposite. D had the lowest frequency, so it has the largest period. A and C were in the middle. B had the highest frequency, so it has the smallest period because they are inverses of each other, exact opposites. Fastest to slowest wave, they should all be equal or the same because the frequency or wavelength or period has nothing to do with the speed. It is totally independent. It is just what medium is it traveling through. And they should all be in the same medium, so it should be the same. All right, a wavelength is increased. So imagine I've got a wave like this, and now I have a wave like this. The amplitude does not have to change, right? Those are separate from each other. Getting longer doesn't make you not have as much height as before, so that's not going to be the answer. The frequency is increased, the frequency is decreased, or the speed is increased. Well, we know the speed is not increased because speed depends on the medium. So now it's just what did the frequency do? Well, let's think about if we have a longer wave means I have a lower frequency, right? I have less waves each second because they're longer than before. So that means the frequency must have decreased. Standing wave, second harmonic. So second harmonic has two antinodes or two little loops. It looks like this. This is a 1 meter long rope. So that means that my wavelength is 1 meter because this is one wave right here. So wavelength is 1 meter. And I have the frequency right here. So the speed, I did not give enough room, equals frequency times wavelength. Frequency is 20 times wavelength of 1. So that's going to be 20 meters per second for your velocity. What is the frequency at the third harmonic? So let's think this is my second harmonic, which means the first harmonic had to have a frequency. This one has a frequency of 20, this one was 10. So this is 10, 20, the next one, the third harmonic, will be 30 hertz. So the third one will be 30 hertz. And the fourth one would be 40 hertz. You're just gaining 10 each time because 10 was your fundamental, which is why the second one was 20. Right, police car has already passed Jaylene, but has not yet passed Anai, and Kaylin is inside the police car. Rank the pitch the girls hear from lowest to highest. So this is like your Doppler effect. Kaylin is going to hear a totally normal pitch because they're not. Kaylin is not going towards or away from the source, which is like the police car, right? Sending those are sound waves. Anai, they're going towards one another, so she's going to hear a higher pitch, and then Jaylene is going away, so she's going to hear a lower pitch. So lowest, medium, high. Here we're going to plug in, we've got a stationary observer, so V observer equals 0. A car approaching emits this this frequency from its horn, so I'm going to say that's the source frequency because that's what the car is sending out or emitting. The observer detects a frequency of 500, so that's the observed frequency. How fast is the car moving? So I'm looking for velocity of the source because the car is my source. So I'm going to plug in FO equals V343. VO is 0 on the top, so I'm just looking for VS right here. And then this right here is source frequency is 450. Source frequency. And then it says approaching, so that is going towards, which is a minus sign right here. Divide the 450 over. So I have 343 over 343 minus VS. And then that's going to give me 1.11. Now I need to multiply this up. So I've got 1.11, 343 minus VS equals VS. Not equals VS, equals 343 when I multiply this up here. Right, divide the 1.11 over. I'm left with 343 minus VS equals 308.7. Subtract my 343 over. And that gives me, and I'm going to divide the negative sign out, so that gives me a source velocity of 34.3 meters per second. Burglar alarm, wailing with a frequency, so I'm going to say that's my source frequency. What frequency does a cop hear? So that's looking for the observed frequency, who is driving towards the alarm at 30. So this is obviously a velocity. Let's think through our source and observer. The alarm is my source, the cop is my observer. So the cop is driving towards the speed, or towards the alarm, so that's the observer that's moving. The alarm isn't moving, it's the observer that's moving, so VS is 30. Now straight plug in, FO equals 343, 343. The 30 is VO, that goes on top, and it said driving towards on top, O towards is a plus sign, And then Fs is on the outside, the 1400. And now I don't need to rearrange because it's already F equals, but I do need to be careful with putting parentheses around whatever's being added or subtracted. So 343 plus 30 parentheses over 343 times 1400 is going to give me an observed frequency of 1522, which at least is reasonable. The original is 1400, and I knew it was going to be higher just going towards. So continuing with this problem, what frequency would the burglar hear if he's running away from the alarm at 10? So same source frequency, but now I'm going to get a different observed frequency because now I'm going away. It should be lower, and I'm going at a different speed. So it's actually pretty much the same question, but now it is a minus because he's going away, and now it's moving at 10. And I need to be careful with parentheses around the whatever's being added or subtracted. Not necessarily what's on top, just whatever's being added or subtracted. So a quick check for us is we know it should be lower than normal because it is going away. And I got 1359 hertz, so that checks out. How fast would one have to move towards or away a stationary tuning fork emitting this tone? So that's my source frequency in order for it to sound as if the tone, so that would be my observed frequency. And this tuning fork is my source right here, and the person moving is the observer. So I'm looking for how fast the observer velocity would have to be. So now we're going to plug in 380 equals 343, 343. I'm looking for VO that goes on top. And then the 390. So let's think about it. If it is 390 and it sounds as 380, it sounds lower, which means you're going away. So for away, on top, away is a minus sign. And then now we're just rearranging to get V naught. So divide the 390 over. So it gives me 0.974 equals 343 minus VO. 343. Going to multiply the 343 up. So then that becomes 334.2 equals 343 minus V. And then now I just subtract the 343 over. So that gives me negative 8.8, and then the negative sign, because technically this is negative V naught, so the negative signs will divide out, so 8.8 is your answer. Doppler effect, when a source is moving away from you, the pitch is going to sound lower because the wavelengths become shorter, more squished together, so shorter wavelengths, and the frequency is higher. Oh my gosh, I said that totally backwards. My bad. Lower, they're getting spread out, the wavelength is becoming longer, and the frequency is becoming lower. My bad. Okay, 4 waves are sound waves, which would be the loudest. So loudest is going to be the tallest wave. So A looks like it's the tallest wave. The quietest wave would be the least tall. So I would say C or D. You can't really tell. Highest pitch. So highest pitch is going to be the one that's most squished together. So it's going to be D. Lowest pitch is the one that's most spread out. So that's going to be B. And the one that is high-pitched and quiet, so squished together but not tall, that's D. Sound changes to a shorter wavelength. So shorter wavelength is going to mean a higher frequency. So a higher frequency is going to sound like a higher pitch. Amplitude has nothing to do with the wavelength. Those are totally separate. Wavelength and frequency are the same because, or sorry, not the same. They are related because this one has to stay the same. So if I decrease this one, see how this one has to increase to compensate? So that's the idea there. The graph below shows displacement of a point in a medium over time. What is the frequency? So remember, this is time right here in seconds on the x-axis. The definition of frequency is the time for one wave. So, or sorry, not the time for one wave, that's a period. Frequency is the number of waves per second. So let's go to 1 second and then count up. 1, 2 waves. So frequency of 2, because you literally have 2 waves in 1 second. And the definition of frequency is the number of waves per second. Two waves are traveling through the same constant container of nitrogen gas. That means they're the same medium, which means they'll have the same velocity. A has a wavelength of 1.5, B has a wavelength of 4.5. The speed of B must be the same as, because they're going through the same medium. What must be true about the frequency of wave A? So, sorry, of B compared to A. So B has a longer wavelength than A, which means it has a longer wavelength is a lower frequency than A. And if you really wanted to, you could say, okay, 1.5 and 4.5. So not only does it have a longer wavelength, it has 3 times the length of the wave. So that would mean 1/3 the frequency of A. FB would be 1/3 the frequency of A. The following wave took 0.75 seconds. So this is the time for this entire picture. It doesn't say specifically period, because sometimes it'll say it has a period of 0.75, in which case you would just do 1/. But this one is for the entire diagram. So to find the frequency, I'm going to do number of waves, which would be 1, 2.5. So frequency would be 2.5 waves over 0.75 seconds, which is that one I cannot do in my head. So it's going to be a frequency of 3.33 hertz. Period is just 1 over that. That's going to be a period of 0.3 seconds. And then velocity equals f wavelength. Frequency is 3.33. I gave you the wavelength. It says the wavelength is. So now you just multiply and you get like 1.5 meters per second. Good luck, study hard.